Start from this week, we are going to talk about some tools and libraries that help you to increase or enhance the performance of your program. Because we are doing data science, we are usually dealing with a large scale of data and involving with some very complex, complicated algorithm that require some computational power in order to do the computations. So Python is not known for its performance because it is a language that is easy to use and has a very great user base for a very large user base, and so it has a lot of application. And apparently, it is one of the most important language that is using in data science or data analysis, machine learning, and deep learning. However, still, the its lack of performance still issues when you want to do experiments. So if we can do the experiment faster, then we can explore more possibility and find more results. But luckily, there are some tools that is in the Python data science ecosystem that can help you to enhance the performance of your program or your code. Today, start from this week, we are talking about some of these tools, including the topics we are going to cover today is the cython and numba. We're not going to talk about JAX. Initially I plan to talk about cover JAX this week, but I decided to move it later, so we can talk about more things related to cython, numba, and other tools for writing Python extensions and to kind of compile your Python code to make it faster. And there are also other tools like Polars, Perl and Rust. Uh, it is also very popular choice for using Rust to write Python extension, just like Cython. We're going to mention it a little bit, but we're going to cover most of the topics in next week. So including the Polars and Rust and maturing. Polars is a data frame library writing in Rust. It is not considered as a drop-in replacement for pandas, but they share a lot of similar functionalities, and it is also very popular. At the very beginning, it will looks and feels like pandas, but it will have certain difference if you dig more into it and use more advanced functionalities. So we're going to cover it next week. And finally, we're going to talk about something related to deep learning and large language models, like JAX, Flex, and also how to serve large language models by using different frameworks like VLLM or Llama, Llama CPP, which is a backend of Llama, and Llama files, and transformers. We'll also talk about a little bit about how to um, do like CPU offloading and the related stuff. So let's begin with today's topics, Cython and numba. Okay, let me reload the slides a little bit. So first of all, let me mention the code, some of the code I'm going to use today. You can go to this repo, GitHub repo, NCTU IOG 5017, and there are some Cython related stuffs and number related stuff in these two directory. You can find the code in here. But before, let's dig into the more technical details about the code. Let me give you a broader view about overview about what the cython stands for, stands at, what the cython stands, where the cython stands at. So first of all, there are some Python implementations like the C Python that you are using, and the C Python is, like the name suggests, it is written in C, which is the Python you are familiar with. But there are more than one Python implementation. So the official name of the Python that you are using is actually called the C Python. It can be considered as the official Python implementation, but Python itself is a language. It's a language specification. It's a language standard. So anyone can use other language or other code to implement a Python interpreter or even a Python compiler. C Python is a standard one. It provides a API called the Python C API, so that people can. There are twofold. One thing is that we can access the Python functionalities, like all the Python useful tools, including the Python standard data format, data type like list, dictionary. They're very useful. So in fact, you can access to these Python data types or Python libraries or even Python code in this C language API. So if you're writing a code in C language or maybe in C++ language, then you can actually include these Python header files and link to these Python libraries so that you can use all the tools that provided in Python environment or even in Python ecosystem. You can even embed a Python interpreters in your C program. So all of this is written in C language syntax. So that's one way to use all this C API. Okay. Also, you can write a C extension. I mean, a Python extension in C language by using this C API. So you can, because if you are writing or developing a extension for Python, you definitely need to communicate with the Python interpreter. So by using this C API, you can write a function or a library that can communicate with Python. So although they do the similar things, I mean, they require similar functionalities, the purpose is not to write code in C, but we're writing something in C, of course, but the primary use is to use these functionalities so that we can import this module that is written in C in Python space. So we want to write Python code, and we can extend the Python functionalities by using these modules written in C language. So sometimes it is for functionalities that is not originally exposed to Python easily, or sometimes it is for performance. And sometimes it is, there are some libraries that already develop or exist in C ecosystem or in other languages, so that we can use this Python C API to write extension to bind these libraries into Python, so that so in Python we can import some module and access to these C functionalities. But there are more than one Python implementation. Another popular one, probably the second most popular one, is PyPy, PyPy. Kind of like the name suggests, it is a Python that is implemented in Python. the logic is similar to C Python. C Python means a Python interpreter written in C, and PyPy means a Python interpreter written in Python. So how is it possible? Or because if you really need a Python interpreter, why do you, if you already have a Python interpreter, why do you even want to implement a Python interpreter by using Python? There are some reasons for that. At the very beginning, it can be considered as a experiment. So even though when we have nothing at the very beginning, we still have a C Python implementation or others Python implementation. So in principle, we can still write a Python interpreter or Python compiler in this scenario. PyPy provides some kind of compiler in it, so we can actually develop an interpreter or a compiler in Python in Python language. So PyPy can start from other Python implementations. So after you implement a Python interpreter or compiler in this form, especially a compiler, then we can use this compiler to compile Python language into a binary executable form. So we exist the first iteration of the PyPy compiler. So after we got this compiler, then we can develop it on this first iteration of the compiler, Python compiler, and run our original implementation. Then we can get the second iteration, and we can get rid of other C Python or other Python implementations, and kind of bootstrapping from the original implementation from PyPy. So in fact, PyPy included a Python compiler, a Python-like a compiler that for a Python-like language, which it is called the R Python. The R is kind of standard for restricted, because if we want to implement a Python compiler, then it is still a very difficult job. Especially Python is a language designed for like in interpret environment. So it is very difficult to actually build a Python compiler for to support all the features that Python has. However, since our primary goal is to use this compiler to actually to develop our Python interpreter or the future Python compiler, so we probably don't need all the functionality and the features in in the standard or official Python specifications. So we can actually just implement the functionality that requires to build a compiler or interpreter. So that's R Python is. It is a compiling language so that we can compile things into executable. And the syntax can be considered kind of like a subset or restricted version of Python. It has a lot of restriction, and because Python is so dynamic, our Python cannot be, if we want to develop a simple compiler, it cannot be so dynamic. So our Python has a lot of restriction, like we cannot, so every object or every variables has to have a specific type, and the type are more restricted. The integers are not big number, are not big integers, just like the integers like int 64, like other language like C language or C++ language, like other compiler language. So that is R Python. It is a more restricted form of Python. So it is kind of like the cython that we will discuss today, because it is a Python-like language and it can compile. It is a compiler language. Can compile your code into a binary executable. Except there's a major difference. RPython is a more subset, can be considered restricted or subset of Python. But cython is a superset of Python. RPython, the goal of RPython is for developing like a new language interpreter. It can be used other than implement a Python language compiler or Python language interpreter. It can also useful for developing a new language. If you want to develop a new language, RPython is one of the choices that you can have to build your own compiler or your own interpreter. Other frameworks candidate are like LLVM or GCC. You can use those of things. And there are also other parser or compiler libraries that you can use. But RPython is designed for doing the same job to develop a new language. But the most famous example or most successful example of RPython is the PyPy, which is a Python implementation. Okay, let's go back to RPython and the cython. The RPython is designed for a more specific application in mind, so it only requires a subset or restricted version of Python language. The goal is not to implement the full standard of Python. However, cython is mostly compatible with Python. So every code that can be run in Python is supposed to be run in cython. It just may not be that fast, but you can still run it and compile it into an executable. It just cython provide some extra functionalities so that you can enhance the performance and speed up your program. So that's only different. That's some difference between RPython and the cython. There are much more other Python implementations like JSON, which is a Python in JVM Java environment, and there's IronPython, which is a Python implementation on .NET environment. There are also MicroPython, stateless Python. MicroPython is target for like edge device, or more like a single board computer edge device. And the stateless Python is an experimental implementation of Python that without stake, so it can have some benefit when running it in Thread or Perl. There are also many other implementations of Python in other language, including Hython. Hython is an implementation of Python in Haskell, which is a functional language, and CLPython. I maybe recall it incorrectly, but I think CLPython is for command list. A command list is also a very popular functional language. As you can see, Haskell is a functional language, and command list is also a functional language. Why is it so? I mean, there are a lot of different language paradigms, but all these two, I mean, the first two implementation in other language are from functional language. Is it a coincidence? Actually, there is a common tradition or a typical application of functional language is to design a new language. Like ML family of language. ML is a family of language like Camel or Camel and other ML language. They are famous for to implement a new like the parser or language compiler things like that. So that's no coincidence that there will be a Haskell Python and the command list Python. Burp is also another one, but I forget which language it is. Maybe let me do a quick search. Okay, Burp is another one. Okay, so it is written in Rust, I think. Let me check the compiler. Oh, no. Okay, it is also in Haskell. Yes. Okay, so it is also in Haskell, in GHC. So it is also implemented in Haskell. The dialog of the Haskell is GHC, which is Goswell Haskell compiler. That is also a very popular, probably the most popular compiler for Haskell language. Also, there are JavaScript variation of Python, like Brython, which we kind of talk about it in last week, and Sculpt. They are all kind of Python dialog that you can run in a browser. More than that, there are also PyJS, transcript. They are more focusing on different purpose, but they are all considered as a JavaScript implementation of Python. And people also like to make Python faster, so like to make Python like a compiling language. So there are also other compilers, some compilers for Python. The one of the early one that I like it is JetScheme. It is a research project that do the auto type inference, and it can transform the Python code into equivalent C++ source code. There are some caveats, including that the integer type in JetScheme is typically like int 64, not the big int like Python. At the Python 2, at least for early Python versions, integers has two format. One is the integer, and when it grow up to big enough, it will become a big integer or long integer format. When it is still like a short integer style, it will be something like int 64. But it will automatically transform into another type when it is getting large enough. There's an automatic checker to check whether it is exceed the bounds of like integer 64. But at some point, it is unified into just one type that is a large integer. So back then, back when JetScheme, there's still like when JetScheme developed, there will still have two types of integer in Python. So that makes sense that the JetScheme only use the short type of like a linear type, like 64-bit integers, instead of using a big integer that with unlimited precision. But because the standard Python is usually considered integer as integer without limit, without bound, which is a big integer, as the terminology goes. So JetScheme will have some incompatibility is incompatible with the standard Python, but for most of the time, it will compile really fast code. Convert to Python to really elegant, in a more elegant way into a into a C++ code using the STL, standard template library in C++. Use all the collections in standard template library to make the code very readable. So that's one of and it can run really fast. So that's one of the tools that I like. But unfortunately, it is not developed. I don't think it is actively developed. And the Python evolved a lot since Python 2. Currently, we have Python 3. So it is very different than the Python 2 era. And there are some alternative to this shared skin since in nowadays. One is I'm more familiar with cython, although it is not that intelligent or that automatic way like shared skin do, but cython also have a type inference, which is the selling point of shared skin, and there are some ways that you can write, which I will introduce in my code, to write Python like you write a cython code in a Python like manner that can convert to a very good C++ code. Although it is not the primary usage for cython, but cython does pick up some functionalities or some features that shared skin have. It is possible to write similar code and get a similar result that shared skin has. Another way today we can use is that we have a large language model. We have very good large language model, and people already do that to transcript one language into another. So I think a lot of functionality that shared skin have, we probably can do it with a large language models, so that we can convert a Python code into an equivalent C++ code to improve the performance. And probably it is have a more can cover more possible Python code, because a lot of code cannot be compiled in shared skin. Another compiler is Nutica. Nutica also can increase the performance of Python a little bit, but I think the improvement is not huge comparing to shared skin or cython. If you write in a more cython way, it is more focused on just compiling the Python code out of the box without modification. So that you can protect your intelligence properties, because when you deploy code in Python, people will see the source code of your program. A lot of time you don't want this to happen. You want to deploy it and given the executable to your client, but you don't want them to see the code, because that's probably something you do is your secret. So Python has these issues. So sometimes people will kind of do some obfuscations so that people cannot see the code and do some encryptions. But Nutica is one of the way, because it can compile Python code into executable. You can actually do further encryption of obfuscations into the binaries, but at least it will, in principle, it is a compiled language, so it will not export more source code into just like the plain Python is. So that's how the Nukita does. Just like a shell scheme, Cython is, and the Nukita, Cython is a compiler language. We have mentioned that Cython can have some overlapping functionality with shell scheme, like improving the performance. It also can do something like Nutika, like compiling a Python files into a executable. As we say that Cython is actually a superset of Python language. So every Python code is automatically compatible in Cython environment, and the Cython can compile every Cython files into executable files. So definitely it can do something like Nutika does. However, because Python is a very complicated environment, when you input something, when you want to compile something, you actually want to compile a whole like environment into it, not just one file, or not just one file. You probably want to compile all the environment into it, all the library it included. Nukita, because Nukita is focused on this application, it will more convenient for Nukita to include all the dependency into one executable. I'm not sure Cython can do this, or there are tools for it. Actually, I'm pretty sure Cython has the functionality or the capability to compile all the modules included in Python. It just I'm not sure there are tools that for you to convenient to pack all the environment into one executable. So other libraries like I think like Py2exe or something like that are also similar tools that pack your Python applications into one package. Also, the Docker can have similar can be considered as has similar purpose because it packs every environment into one file. This is especially good for Python or in like for deep learning applications, because when we consider deep learning applications, we usually want it to include all the NVIDIA libraries. So it is more than just Python itself, Python environment. It is including all the other supporting libraries and the executables. So in this sense, Docker is also aiming for the similar application. So that's all something that you similar to what the Nutica can do. But for Cython, it's mostly for the performance, as far as I know. Okay, and there are other things like numba and PyStream, and also module. Module is also a compiler language. I haven't put it in. I put it in later, that as an implementations. But module is also similar to Cython because it is a compiling language, and it has some extension to the Python to a Python. So in that sense, module is similar to Cython, but module is a more commercial product. Unlike most of, all of the implementation I mentioned right here is open source. Some of them may have the commercial, a company behind it, a commercial company behind it. Maybe like IronPython was originally developed by Microsoft. I'm not sure JSON, but anyway, all of these things, or maybe some of them are backed by some startups, but all of them are, as far as I know, they are open source. But module is closed sourced, and so that's the difference. A numba and the PyStream are just-in-time compiler for Python, and for future version of Python, or currently they already have some implementations for experimental features. The official C Python also have just-in-time uh, compiling functionalities, but numba and PyStrength are kind of like a transcoder or a transcriptor for Python to convert into a more efficient language. So there are also JAX. JAX also have a just-in-time compiler things, and some of the CUDA implementation of Python also have similar things. So this is definitely not a complete list of all the libraries have similar functionality. So consider this as a start point or not a complete list, because there are a lot of, but you can see that there are a lot of attempt or interest in improving the efficiency of Python. That's why we have so much different implementations. There are also similar language, which is cython can be considered one of the similar language, but it is a superset of Python. But what I'm trying to list right here is other language that are similar to Python. So probably module should move to, because for a comparability of module, it's more comparable to Python. The other language that I mentioned here, like Bool, Nim, Genie, are a lot different than. I mean, they have some similarity to Python, but not the level of module or cython or RPython or even my HDL. My HDL is more like Python, but it is aiming for like HDL things to writing kind of writing hard word description. So it is because they are aiming for very different functionality. Their application is very different. So although the aim of my HDL is to make the syntax as close as possible to Python, there will be some differences and some extensions. So let's just see the language itself so you can judge it by yourself. The first one is Nim. Nim language, you can see that it has import something like Li1, and it also has the significant space and use indent to structure the code, sort of like Python. You will see very familiar in this code. This is totally fine Python code, but you definitely can see something new. For one thing, it uses echo instead of print. And like the original Python, the print does not have a parenthesis. Does not need a parenthesis. It just print and something right here. So it's more like Python 2. Because back to the time Nim was developed, it was still the era of Python 2. I'm not saying that Python 3 is not existing, because Python 3 exists for quite a long time. But like 10 to 15 years ago, when people talk about Python 2 still is still a thing, and a lot of people use it. Okay, so also you can see that there is a const. So because it is a compiling language, so it makes distinction between constant and other things to improve the performance, so that we can improve performance. And also one of the great feature that people always, developer always thinking about is the macro. Macro origin from the from Lisp. Lisp language, there's a macro. It is meta programming features that you can modify your language to make it have new syntax or new semantics. it can, so consider macro as a code that can handle the code. So it can transform the code into something else and run it. In Python, we can actually do that because Python has a exec function that can execute anything in a string. So Python, I mean, if you really think about this functionality can be implemented in Python, but in the philosophy, design philosophy of Python, readability is very important. So macro or other metaprogramming techniques may make the program kind of unreadable because you can always implement new functionality into a language that people is not aware of. So that will make reading the code more difficult. So the philosophy of Python is more toward against metaprogramming things like macro, but it is actually doable. So you can see that the name has macro because a lot of programmer want to kind of customize their own languages. The macro is one of the more powerful tools that you can customize your language into your needs. You can still use your favorite language, but you can customize it to your own need to make your own language. You can imagine that if everyone has their own language, then there will be a lot of different variants of this language. So Python, in the philosophy of Python, it sort of against this idea. Although it still want the language to be very convenient to everyone, it's against the metaprogramming things to an extent so that every code is still readable to everyone. But like I said, a lot of developers like and want to have macro or metaprogramming features. So Nim is a language looks like Python, but it has a macro. It has a metaprogramming features, and it is compiled language. It is a compiling language. Other language like Julia also use a lot of macro, like also Lisp. This is my HDL looks like. It looks like a totally fine Python code, but it will have some unfamiliar decorators. You can see right here, because it is used for like HDL, like hardware describing language. So it is using in Python syntax, but sometimes because it has a totally different purpose, it will have some limitations and unfamiliar decorators and functions. So this is my HDL, but it looks totally like a Python code. This is a module. You can write Python code in module like this one. This is a Python function, like subtraction one number from the other. But you can also write it in Fn to define a module function and give a type hint. So it is supposed to compile this function to make it run faster. We see a lot of things similar in numba and cython, but this is what the module code looks like. This is Boo language. You can see that it is also has things like Python, very similar, very similar syntax to Python. But also there are something unfamiliar, like using a dollar sign for formatting, string formatting. Because back then Python doesn't have much formatting syntax. This is before Python inventing the F string things. So they use this dollar sign for a string template. So there are some differences, but it can be considered as a Python-like syntax compiling language. So also you can see it has typing. It is also back before the type annotation, type hint is designed into Python. So it has its own way to annotate the type of each variable. I use both a little. I forget the bool. Bool is probably is probably a JVM or .NET language. Probably JVM. So I used it back then when I developed something, but just for a little while for fun, because I was more familiar with Python language than probably Java or maybe C Sharp. So that was one purpose of it. But I didn't hear it a lot recently, so I'm not sure this language is even relevant by nowadays. But it is still very interesting language that you can see people are attempting. People like Python so much, they are attempting to kind of convert other language into a Python-like syntax. Now this is Genie. Genie is a language for GNOME, like GNOME. That is a desktop environment GUI system. GUI desktop environment system, like using GTK. There is one language called Fala, VAL. I forget it, Fav or Fala, VAL, VA, Fava, or maybe Fava. It is more like a C language style, the C syntax style, but it included some object-oriented features into a C language. You can consider it as kind of like a C++, but not C++, because it's using the GTK G-object system. GTK is a GUI framework. It is using C as a developing language, but C is not an object-oriented language, so it has its own object system, probably called G-object. So although it is written in C, GTK is written in a more object-oriented style. It just because C language lack the features for object-oriented features, capabilities, but you can still write it in object-oriented style. It's just a little bit more complicated than that. So Fav is using this object system that is developed in C language and add some more convenient syntax. And Genie can be considered as a Python syntax version of the Fava. So it also use the same object system, the GTK object system, G object system, but in a more like a Python style language. But I think because it is in the underneath, it is still a C-like language. As you can see, that C language has a main function as an entry point. Python, notably for its hello world things, it doesn't have a main function. You can just write one line print quote hello world, then it can run. So it still want to capture this convenience or vibe, or this kind of Python vibe. So you can see that although it has a init right here, other than that, everything is more like just one liner. You can just print hello world right here. Just discard this init and these locale selections. It's just like Python. You can print hello world, and as you can see, it doesn't have a parenthesis right here. So it's more like a Python 2 style, because this is also developed back when it was Python 2. After the Python 3 introduced, I think all these attempts are ceased existing. I mean, the only language that after Python 3 become popular, and the I mean the Python like language after Python 3 become popular, it's probably just the module, the Julia. It is because the Python ecosystem is becoming huger. Probably people, I mean, there are probably some reason, because one of the reason is probably the early adopter is more exhausted for Python. So they are so exhausted, and because they are early adopters, so they have their original environment like JVM, like in this case they have a GNOME environment, and maybe like C# .NET environment, because they have their original environment and they are so exhausted with Python. So they want to kind of transport this Python vibe and the language style back to their own ecosystem. But after the Python 3 become popular, probably people are already Python native people, so they are nowhere to go. So that's probably one of the reasons. So the language that sort of Python influenced is after the Python 3 getting popular is probably just module and probably Julia. But Julia has its own language. It's totally different language. So although it has some Python influence, I probably cannot say that Julia can be fall into this category. But if we including Julia, both module and Julia are aiming for like machine learning, data science, or deep learning environment. So that's, I think, the motivation of maybe Julia and the module are different than those like language that we mentioned before, like a Boo language, Genie, or even with the High Python, CL Python things, or like NIM language. They are different purpose for different purpose. Okay, so the similarity between this language and cython is that cython is also another language that sort of like Python inspired language or Python-like language, but it is very like Python. It is a superset of Python. The difference between cython and this language is cython has a very long history, probably even before or about the time of this Boo, NIM, and Genie things, and perhaps even earlier. And unlike them, cython is developed for like numerical analysis in mind, and it is still relevant in the era of data science or even with deep learning and machine learning. So that's the kind of a difference. And the cython is aiming more to the, at least for beginning, is more aiming to performance and extension development. So that's the difference. So, but you can see that cython has, originally cython has some features and some behaviors more like from the Python 2 era. Even when we enter the Python 3 era, it still left some features like print. Originally, it's only supported like Python 2 style print, so that is without parentheses. But now it is more like Python 3 version. Okay, so let's go to the tools that we can write C extensions. Here is a non-complete list of tools that we can write C extensions. Let's look from the last one first. The Metriring is a convenient module that for Rust to write Python extension, which we'll probably will mention it talk about it in next week. And also there are cython. We are going to talk a lot about it. We didn't need write numba, this number here, but number can also write extensions. PyBind 11 is a very popular and one of my favorite way to write C++ extension for Python. I use this a lot. I didn't use Swig, but Swig is also very popular to write extensions to maybe many other language. It is called simple wrapper integration or something. But it is aiming for writing things in a more convenient and simple way. CFFI stands for C Foreign Language Interface. Foreign, I forget, foreign something interface. Let's check it. Okay. Foreign function interface. Foreign function interface. So it stands for foreign function interface. It supports two API. I mean, the most two popular Python implementation is CPython and PyPy, but they have different API. Python is C API and the PyPy is called CFFI, but CFFI is also supporting to write extension for CPython. So if you are using CFFI, you can write extension for CPython and the PyPy. So let's first talk about what the Python C API is. Because cython is also targeting C language, so C++ and the C language. So the CPython C API is also very related to cython. If you want to dive into the cython, you will have to understand what is provided in the C API. And in fact, if you look at the code generated by cython, you will see a lot of C API code. So it will help you into understand what the code is. Also, at the beginning, you define something or include the python.h. You include the python.h. So this is a C code that to call in C API function. It is readable, but it gives you an idea that you can write C code to access to Python object by your own code. So first we define a py object pointer to something. Then we use pytuple_new to construct a new tuple of three. Because tuple has a size, so it has three components in this tuple. But as you can see, in this type, I mean, we have different data type like tuple, list, dictionary, or maybe integer, floating numbers in Python. But this type exists in Python environment, not in the C environment. In C, they are all same data type called the py object. They are all py object. So the compiler will not know which type it is. If you are using some apply some functions or method that is for tuple on another object that is perhaps a dictionary, it will have some exception. But because Python is a dynamic language, you don't know which. I mean, in compile time, you don't know. In principle, you don't know what type it is. So that's why all of these things is determined in runtime. So in fact, if you have a loop, you can first assign the t to be a tuple. Then next, you assign t to be list, and you in the next time you can assign a map to it. I mean dictionary to it. It is possible. Okay, so that's a distinction, and you need to understand about the difference between the C word and the Python word. They are different. So but the code is quite readable. The first line is that we construct a tuple object with 3 components, and we can use a set item to set the first item to become 1, and the second item to become, first icon to become 1, and second item to become 2, and the third icon to become a string. But all of them are Python objects. So not only it is a number, it is a Python long format number. So it is just Pylong. But we have to initialize this Python long number somehow. So initialize it from a C long number. So it's called 1L. L means long. In C, there are different integer type like int 64, int 32, or int other things like int 16, like a short integer. So usually the 16-bit is called the short, the 32-bit is called the long. But it is not a standard. Sometimes they will have some confusion. There are more modern way to actually specify how many bit the integer is, like int 64 t or other things. So the longer is probably 32-bit integer, but it really depends on the platform, because we are more used to use the 64-bit platform. But anyway, it is from the long integer in C language. So we construct a Python integer and a Python integer. Also, we construct a Unicode string, Python Unicode string from a C string. So you can see that from string, but this is a C string. As you can see that in Python, a tuple is immutable, so that you cannot change the item of it. But we are in the C space, so we are construct it first and set item of it. And this is another way to construct it in a more convenient way. So we use the py build value. So instead of writing it in this this way, that is sort of incompatible to what you used to in Python. Because in Python, you cannot even do that. You cannot assign a value, change your value of a component in a tuple. It is immutable. So we write it more like what we do in Python. We can do that. There are some convenient tools and functionality in the C API. So we can py build value. So it is a list, a tuple or a list, and we can assign the data type like integer, string, string, as we can see right here. So the C API provides some fundamental like the entry point API that you can access to the Python environment, Python object, and also it provides some convenient tools that allow you to write C code similar to what you would do in Python. But you can see all of this has using the same function because they have the same type in C. The C doesn't know it is a tuple or list. It is same object. It just the type information is in the structure itself. So here is a code that you can write. To do things in C API, but of course you have to write in C language. The this is S size. Means this the size of something. Most of the time it is just integers, but because we are iterating from like a sequence, so this is using a type called the size, and because this want to compute the summation of a sequence. So we use long total. This is in C language to do the accumulations. So each item, we construct a Python object to take every item from this sequence. And so this n is the pi sequence length right here. In Python, there's auto. I mean not Python. In C++, it has some type inference capability. So in fact, in modern C++ language or even in C language, you can use the type length to omit this type to make it to be an auto type. It is possible to do so. So we'll make it more like a Python. So this one is just like you can use pi sequence to get item, to get the item itself, and to check whether it is a number pi long, whether it is an integer. If it is, then we take this item and get this long, get the value of it, or get the value of it, because originally it's just an object, and we get a value of it, and we get it like a C value, and we can add this value into the total. But the interesting thing you can see here is a pi dec ref declares the reference of this item. The thing is that most of code is sort of easy. Even if you are not familiar with C language, you can still see the logic of everything. Pretty much mimic what the Python does. They have a slightly different syntax because we have to call the C function right here, and does not use the square brackets to access the item, but they are pretty much have a similar logic. But the difference is you have to check the type, and also you have to manually manage the references. What is references or reference count is? It is because Python is a garbage collection language. It has automatic garbage collection, but the C language does not manage the memory for you. So you have to do it in a more manual way. There are different ways to manage memory in C language, and there are different frameworks I can use. In here, because we are dealing with a Python environment, we are using Python to manage the memory for a Python object. And how does Python knows which memory should we keep and which memory we can release it? It has a reference count. If this object is being used, then we should keep this language. We should keep the memory for this object because it is used by other variables. So every time a variable is corresponded or connected to this object, we add a count, and every time it is unlinked to this object, we decrease count. After the count is being zero, then we can safely release the memory for this object. So we need to have a reference count for every object in order to maintain the memory, to manage the memory. This is one of the reasons that we need a GIL, global internal lock. It's because we use this reference count a lot. So we have to, every time we are using Python object, we will need to look up the reference count table in the Python environment. So if you are using Python object in your code, the reference count will kind of update. So if you're working on a multi-thread environment, so most of the time we need to lock everything, because it is very possible to modify the reference count. Although it is doable to do a more fine-grained management, I mean, you can lock in a more small case if you analyze it carefully, but it is very difficult to do so. So Python introduce a global internal lock. So every time if you are going to access to Python object, it will lock the GIL, and after lock the GIL, most of the time you are going to access when you in other threads you are probably also want to access to the Python object, so you have to wait the other thread to release the lock before you can keep going. So that's one thing that is very difficult. And also the reference count is not a solution to every memory management issues, because there are also the circular reference things, like A is reference to B and B is reference to A. Although they are not, A and B, both A and B are not used anymore. Suppose they reference to each other. Consider A is a subject, it has a property that is like point to B, and B has a property that point to A. Like B is a component of A, and A is a component of B. Both of them, suppose both of them are released. It is doable. In this case, although they are not both used, they still have a reference count 1, because A is reference B, B is reference A. In this case, they will be not moved by. If you only use the reference count, they are always keep, but they are not used. So there are many issues need to be considered. But anyway, in here you see that after we access to this value, you have to manually tell the Python environment so that, okay, we have done using the item. You can release the memory used by item. Not just release, because when we do these things, it will increase when we do this thing, it will increase a count, because we are using it to, we get this item, so it is going to reference by something else, because item is a Python object, so it increases the reference count. So after we get this value, we don't need this item anymore, so we have to decrease the item. If you forget to do that, after everything is finished, the Python will still think someone is going to use it, and it has not finished using it. So it will become a garbage in the uncleanable garbage in your memory. So that's why it is always very difficult to maintain and manage memory, and sometimes you'll see memory leak in some C extension in Python, because it is very difficult to maintain everything. That's why Rust is getting popular, because it is a compiling language and people are forced to writing the code in a more desperate way, so that this kind of thing will never happen. But when you write in C code, you will have to be very careful to keep track all the things that is getting referenced, and decreasing the reference when it is needed, when it has to do so. But you cannot do it too early. If you do it too early, sometimes it is still fine. But suppose it is decreased, and probably Python will sometimes check, and it will be garbage collect. And after you do want to access to this item, it will have some memory exceptions right here. Okay, so let's talk about the C API stability. Because C API has some compatibility issues, the typical compatibility rule is that if you have the major revision number like 3.10 something, they are compatible to each other. But this only works for the stable API. There are other sort of APIs that more that some of them will break the compatibility, and some of them are going to have more relaxed compatibility. But the general idea is the Python compatibility is up to the major revision, like 3.10 something are all 3.10x are all compatible to each other, but not to the 3.9 something or 3.11 something. So that's why if when you have a wheel file, when you use a pip install and have a wheel file, the wheel file is going to have a major revision number come with it. Like this wheel is for 3.10, this wheel is for 3.9. So that is for the stable API. For most of the case, the compatibility is for like the major revision only, and you can have the compatibility between if these two versions have the same major revision, but not across the major revision. But there are some other API. One is called the unstable API. So this unstable API is not guaranteed to have capability, even inside the same major revision. And there is also limited API. Although they are called limited, they have more flexible compatibility requirement. So this is a smaller set of API, but they are working across the major divisions. I mean, compatible across. I'm using the wrong terminology. Across a minor release. Okay. So that's the differences of them. So sometimes you will see that some binary is compiled for like 3.9, but it works for 3.10, also works for 3.11, or even for 3.12. That's it, because there's some way to make it more compatible if you are using a limited API. There's also a standard library in Python called the C types. It works very well for calling C functions. So it has some functionalities in like cython or other extensions that allow you to actually load the libraries, binary libraries, dynamic libraries in your system. So most of the time, if you are using a C library, writing code in C function, in C language, the function that you're calling is actually compiled into a shared or dynamic libraries. So if we can have access to these dynamic libraries that is provided by an operating system, or maybe provided by some libraries, third-party libraries, then we can probably have most of the functionality of that the C can do. And because Python has C types, it allows us to load the dynamic library or shared library. So in principle, everything C can do, Python can also do. Every functionality, like coding the operating system, like system call, coding the operating system function call, it can do that. For example, if you are on the Windows, we can use C types to load, because we import everything from C types. There's something called a WinDLL. That is Windows Dynamic Library, and we can actually load the kernel 32 to have everything that is in the Windows system. So you can access all the operating system functionality directly from Python. Of course, C types itself is written in C language, and the Python itself is written in C language, of course. But because this is one of the standard library in the Python, so we can say that Python can access to very fundamental low-level functionality in the operating system. And there's also CDLL, because The C language has a standard library, and this library will have the all the standard functions like printf or other operating system calls or uh, just everything in like mathematical functions like or everything else. Because this example is on Windows, um, this CDL is depends on the C library, and mostly because depends on the C library that is um, in your environment. So in this case, the CDL is MSVC, Microsoft Visual C runtime, or it has a Visual C runtime. So you can access to the CDL that is all the runtime functionalities in C language. But this is, I mean, let's just see the functionality. Like this is on every platform. Every C language has a printf functionality. It works like a print. So let printf is equal to libc printf. So we can use this printf to print the string. Because in the C string it is a binary string, not a Unicode string. So we need to put a prefix b in front of the string to indicate it is more like a C string, a binary string. And printf is a variable argument. So you can put arbitrary number of argument inside it, and every argument can be in different type of different data type in different data type. Okay, so like you can see that here is string, and here is a Unicode string, and here is a integer. It is an integer. The way that printf knows this is integer is from this percentage symbol. The D stands for digit, so it knows it is a number. S stands for string, so it has a capital and lowercase string to indicate different type of string. So it knows this parameter is a string. Otherwise, because it is no type, it's more like a pointer right here. So the printf, I mean, in a C function, it does not know what the type is in the compile time. It's not that smart. So you have to use this special designed format of a string, like a protocol, to indicate the type of it. If you are using a wrong type right here, it will cause the malfunction of this printf functionality. So for example, if you are using 42.5 here, it is 14 number. So it will have a difficulty to do so. So you can actually make it to be a double because it doesn't know. I mean, originally, if you didn't give a type hint, it doesn't know how to convert these things. But if you are sending it as an integer, it will send it as an integer. And if you are sending it, wrap it by C double, this is provided by the C type functionalities. You convert to a C types specifically, then you are going to get fine because otherwise the C type doesn't know how to convert it. I mean, convert the Python data type into C language type. So you have to sometimes you have to manually give the information to let the C types know how to convert a Python type into the C environment. So this seems to be kind of convenient, but so there are some difficulty. I mean, in practice, one is that sometimes the definition is very complicated. Sometimes because Python, I mean C have a structure, and C++ has some class. There are some compound definition of the data type, and also C has some defined macro. So it is not actually easy to convert them into C type format. There are some tools to parse the C header file to generate the definition, but it doesn't always work. So although it seems to be really easy to do so, sometimes you will face some difficulty. Another issue is that in the ABI C++ ABI, that is a binary format of the library. Because C++, in the C API, it is quite easy because if a function called printf in the dynamic library, you will use, it is very easy to use the name alone to find the compiled function in the library. But in the C++, it is different because C++ can have overload function. That is, you have the same function name, but if it takes double or integers or float number or a string as input, or you have one input, two input, three input, a different type of input, it will dispatch to a different function. Sometimes it is a template, so it will compile to something different. It is not even in the binary library, but that's considered as the overload, type overload. So even with the same function name in C++, it will have represent different binary function in the library. So the name alone cannot help you to find the function. You have to also know the type of it, and it is mangled, so the name is kind of like encrypt code. So it is difficult to actually find the name. And even if you know the rules, it follows a rule to, if you know the argument type, know the function name, know the class name, there's a rule to construct the function name inside the library. It's just the rule is a little bit complicated, and it actually depends on different compiler. Like if you are working on Windows, there are probably a different rules to do that, and if you are working on Linux, there are probably a different rule. If you are in a FreeBSD or in Mac, the rules might be a little bit different. And if you are using a different compiler, the rules might be different. So that's a small issue that when you use C type. So it makes it a little bit difficult to actually use C types in practice. But in some prototyping and quick testing, C types allow Python to be a very useful tool to testing, even with some operating system functionality or low-level functionality, because you can actually do so. So sometimes I use Python to do some experiment to access to some Windows API that I'm not familiar with, like extract font from the memory, or like access to some windows, like doing screen capture and doing like automata things, like doing the click button into window. A lot of similar things, like sending a window event to another window. All these low-level things can be done in Python by using C types, because it has access to all these things. So whenever I want to try some new functionalities in Windows API. When I say new, I mean the functionality that I didn't know knew before. They probably exist for quite a long time. But when I try something I didn't know, I want to learn some API, I can use C types to do so. I rarely do this for like in Linux. I haven't have an opportunity to do that in Linux, but sometimes I will do that because I can access to some library function. I will do that, but I haven't do that for OS since because I don't know why, but because I didn't find it necessary to do that, except perhaps for like sending like click button things to other Windows things. But I think they're more convenient tools so that I don't have to use this method to try things. But anyway, in principle, you can use CIPes to do a lot of things, especially if the library is in the C language. It's written in C language, not in the C++ language, because it is, the name is mangled. It's more difficult to access to it. Okay, so what is a CFFI looks like? CFFI is also just like C types and the cython. CFFI is a bridge between the C word and the Python word. So here is one thing that you can use it sort of like what you can do in part of the cython functionality and part of the C type functionality. So one thing you do here is you actually find a definition in just like what you do for the C types, but you are using the C code right here to do the definition. So and like C types, you can open the dynamic library, like loading the dynamic library, and you control the argument right here, and you can call the function, the printf function here. The difference is that it is using C code to do the definition. This is C definition. You don't have to define it in C types. That is one of the difficult part or tedious part for C types, because you have to, when you define the types of like this function, or the C.printf is kind of like libc.printf right here. This for this part is same. The difficult part is to define the type of it. We didn't cover the type definition, but in C types you have to define it in a Python language way. Sometimes it is easy. Sometimes it will be getting tedious. But here it is easy because you are using C language to declare the type of function. So then you just call it. I think this one will getting it more easier because you can use sometimes it's easy. You just in this case it is quite easy. It's constant. In this particular case, in this case per se, I would say that perhaps the C types is easier and more readable because you can write it in Python syntax. But sometimes in a more complicated case, it will be very difficult because they have some define, there are some other things. It will be more complicated. So we appreciate that CFFI can actually help us to do some parsing in the C language. For the functionality part, it is quite similar to what we have seen before. It's just called a printf right here. Another way is to do that is you can actually define a C type like using C language. So you can make sure that this type is more low level. It doesn't have any, in here, it doesn't have any type information. Because when we control a new Python object, it will, from the C point of view, we have to store the type information dynamically. But this is a C type, so it will only occupy the memory of 3 characters, like 3 bytes RGB here. So this is a new type in C. And we can control an image that is new type here allocate like 800 times 600 of this data type. So it is a C array, very predictable. And we can actually just, because of the buffer, this is a um, Python protocol to represent a continuous language, memory sequence, continuous memory sequence. So like in NumPy or other things, if you are using the buffer protocol, you can actually communicate different libraries that is very using a large block of memories quite easily, because they are just a segment of memory. So we can actually read into everything into this image. So but be careful, because the memory only has like 800 times 600 items in it. So this data has to match the size of it. It cannot exceed. If it is smaller, it's probably okay. But if it exceeds the size of this one, you will have a memory leak. And after we do that, we can have the convenient way to access every element in it. So that's one way to use FFI, even if you are not aiming for too much of the C functionalities. So you can actually write extensions in for Python. For one, this is a simple way to compute the calculate the approximation of the pi constant. This is written in C language. So we have a C function pi approximate. The idea of CFFI is that all the declarations is, although we are using this inline, but these declarations are in Python, not in C. The cython, the declaration is in the cython, and the C code is also written in the cython syntax. But they are putting them together. But here, this is a pure Python, not just pure Python. Also, this is a declaration of the interface itself, so we can know that it's a float, return a float from integer for telling the precision, how much precision it required. And the source code is right here, and you can build the things. So you can Python build the everything, build an extension for you. And then in Python, we can import the pi approximate from the module, just run it, and you will see that it will run as we expected. So you can use this way to write a C extension using CFFI. As you can see, this code does not have any Python. Unlike CAPI, Python CAPI, this function does not handle any. It's not. It's just pure. It is just pure pure C language function. It doesn't know anything about Python or the conversion. Communication or bridging between the Python word and the C word is defined right here. So that's the differences. It will have a wrapper around this function, so help you to convert the data type, Python data type to C data type, and from C data type to Python data type. It will help you to do so. And also, as I mentioned, PyBind 11 is a better way to bind things in to build C extension for Python. It has some convenient ways to more C++ way to expose the Python class. So I use PyBind 11 when I write C++ code. So compared to Cython, Cython also has some functionalities that help you to write C++ code. So that's the similarity, and it also, of course, writing the Python C extensions, C++ extensions. except the difference is that when you use PyBind 11, you are writing it in C++ language. So if you are more like familiar with C++ language, PyBind is the thing, one thing you can go. But of course, you lack the flexibilities that to switch from running this code in Python or in compiling it in C++. Sometimes you want to do that, and sometimes you probably don't need it less because you already know which code should be run in C++, or sometimes the code should be run in Python. In that case, PyBind provides a very good way, a very clean way to do the definition of things in Python world. And I mean, this code is define a Python class here. This one is the original struct in C++ world. This is a C++ struct, so everything is in C++. And you use this code to bind the things into something that Python can understand. So this is a Python module. It contains a Python class, which is called the pet. It uses this pet structure right here. So comparing to CFFI, CFFI does the binding things in Python, but PyBind things do the binding things in C++. So you can understand the difference, and after you understand the differences, you probably can choose something you prefer. It all depends on your test, or the requirement. Sometimes you work with C++, it would be better. I mean, if your code base is C++, I think PyBind is a perfect choice for you. I'm not that familiar with Week. It's WIG. So I cannot say it is easier to do this in Swig or not, but I really like PyBind when I want to make a binding, a Python binding to a C++ library. I think this binding is really easy to write. I do encounter some version incompatibilities and some memory leak things when do the porting, but I expect these things will happen in almost every solutions. Cython probably handle it a little bit, but it still sometimes have some issues, their own issues. I'm just saying, although I really like it, but if you encounter some difficulty when you do the pi binding, it always happens. It is something that happens to everyone. But I think PyBind is already a very good library that can combine provide a Python binding to a C++ library. So here is an example of what we have done right here. Then you can import the example directly and construct the pet class. This is a wrapper, wrapped version of the Python, C struct. So it has the same functionality of the original C++ struct, but we're working it in Python. We can get the name, set the name, and do everything. Kind of like here. But we define the set name right here to call the, this is actually what you do here. You can replace this set name by other names like set name 2. And you should call it set name 2 right here. And it will call this function. And PyBind also provides some functionalities so that you can use the Python object in C++, like the C API. So for example, we can use the module to load a decimal. This is in a standard library, decimal in Python. We can load this decimal class, which is quite useful because it have arbitrary precision of a digit. unlike the float or double, they are more working on a binary representation. The decimal is working on a digit representation of number. So sometimes you want least precision, like a 0.1 plus 0.2. In a floating number, you are getting something weird like 0.3, 0.00004. But if that is because there is no accurate representation of 0.1 in binary format. But in decimal, we can represent everything in digits. So you get exactly what you 0.1 is in this. There are no accuracy issue. So this is very useful tools exist in Python, although I believe in C++ there are equivalent libraries there. But you suppose you are more familiar with Python. You probably sometimes you want to use these libraries in C++, even if you are working in C++. So you can actually load this class as a Python object here. You can construct a pi here, like a decimal right here. Then when you want it, you can convert it into something that like a floating number after you do a very complicated computations. Sometimes you want to use it directly, maybe, but sometimes you want to, like all the complicated and dangerous part, I mean the numerical part is over. You want to convert it, the final output, into a double or floating number into C++. You can do that. And sometimes you can use Python modules because the Python has a huge ecosystem. Sometimes it is so difficult to do something in C++ because no one is written the library for that, and you can do that by using here. Like in this case, it's probably not the best scenario that you should use, but suppose I can still imagine that some people is more familiar in Python. Someone just don't know how to make a folder in C++. Then you can use this case to call the Python functionalities here and run everything else in C++. So this is also a way, I would say not very common way to do that, but sometimes all you need, you didn't mind the C++ syntax. You actually like the C++ syntax, and you want to write a lot of code in C++ for the performance, but you don't want to know install too many libraries for some of the tedious functionalities, like here, like maybe like a GUI or other things. You want to handle some non-performance styles in Python. Then you can use PyBind tools to do so, to call Python functionalities. And for more performance critical part, you can write them in C++. Okay, so let's go to the functionalities of cython here. So the first one is to write C extensions without using C code. Although they are converted to C code, but you can write in more Python-like syntax. So in fact, in cython files, usually it has an extension called the pyx. So you can totally write everything in Python syntax. For example, print hello is perfectly fine for writing a cython. It's a perfectly fine cython code. And after you write this is pure Python to tell the Python how to build this file. There's other way to use command line tools to do so, but this is one way to actually how to build the code. But it seems to be a little bit tedious, but usually you don't need to modify a lot. You just keep this one and run this code here, it will compile it. Run this code here, it will compile it. So when you import the hello world here, it will load the hello world right here. So that's how you write extension. This is how you write extension. So the only thing left is how do you actually write the cython code to make it faster. Do I have a link right here? Oh no, I don't have a link. So here we are going to the code in the repo. So let me go to the code right here. So here is a code in a repo. You probably will see in the cython up repo that we provide in our slides at the beginning of the slides. Let me link to the repo so that you can find the code. Although the code has been modified a bit, but you can pretty much follow the code right there. So in the NCTU IOG 5017, you do the cython intro here. You can find all the code right here. The code I'm currently using is in the module, I think, in the module. And in the, you can follow the introduction to the cython to see the basic things. But I'm using the quick prototyping here for the first one, type annotation. I will cover the first one, the second one. Okay, so let's see the code right here. Let me put it in a more bigger, larger font. So there's a really good Jupyter Notebook extension. I know IPython Notebook extension called the cython after you install the cython, which will help us to explain the code. So here is a Python function here. If you are compiling it with cython, it is fine because it is totally by using this IPython magic. I'm going to compile this code, and you can see that the yellow part means it remains to be slow, which is a more Python compatible style to compile it. If you really expand the code, you will see that it will using the C API, Python C API to run the thing. So every Python code is compilable. You can see that it will make it into more like C code right here. You can see how it compile into a C code. So everywhere where you can see that it is more like a C API things that sort of wrapped into the Python cython extension here. So it is more like convert Python code into a C API equivalent. You can see like the PyNumber multiply, which call the C API function of PyNumber for the Python number things. Also, there is also like decrease the reference things and add the number things. It is runnable. You can see that the type of this file, this function f is a cython function. So you can actually run it. Let me run it. Like 10. Probably I can do that. So you can just run this random Python function like here. So it's runnable and it already a compile function. So you already write an extension in a C code. It's just not so efficient. So if all you need is write something in compile mode, like in a binary mode, like in a shared library or dynamic library, then you are already done it. It is not that efficient. The goal is here in this notebook is to make it more efficient. So we want to eliminate all the yellow things to make them into white. and it is not difficult. All we need to do is do some annotation. So we annotate this x as an integer, so that the cython knows this is an integer. You can see that is all we do. We make it to be an integer here. You can also use the Python type hint, but the cython was developed before the Python annotation hint annotation has been introduced. So it has its own type annotation syntax, more like a C style. So it is in front of it, not behind the variable. So let's see what we can do right here. Comparing to here, it's pretty much similar. It is similar. So, it already knows that you can see a difference. It knows you probably cannot see much difference because this doesn't help much. Probably we didn't make many type of inference right there. Okay. So we have to do more type of inference. I mean, to do more type of annotations. Let's put the I, Y, Z, all of them into some, give them also integer type, so that the cython know, okay, they are integers. They are integers. I mean, these integers are C integers. So all I do is cdef. After the cdef, since it looks like a C syntax to do the definition, so we know that I, Y, Z are all integers in the C language, like C integer. So after we do the type of annotation, although the functions still works pretty much the same, like f. So this is f0 cython function, and we can still do things like this one. But if you're doing this one like really long number, it will fail. However, if you do here like here, you do this one and go back to this one, it should work fine. It should work fine because we didn't change the type of this x, so everything is a big number. Big number is one of the reasons that Python is slow. But if we want to make it fast, we want to become like a 64-bit integers. So it will become faster, but it will not work with big number. It can still work like something like this one. This one is still in the range of 64-bit numbers, so it works right here. Okay, so but by doing everything in, declare every, is probably a little bit tedious. Sometimes if you are not familiar with C type, it will be difficult. A thing is that you can use this director to ask the cython to do the type inference automatically. So I only give the type of the input. It will infer the types of other variables. So you can see that I assign y to be x, z to be 3. So it will automatically kind of inference that, okay, because x is an integer, a C integer, so the y should be also be an integer. And this is a number, it is an integer. So z, because of this directory, I am free to assume that z is also an integer. So after I do this, although I only modify the input type, everything else is going to be white. Everything going to be white. So we can maintain the elegance or cleanliness, shortness of this code, but we still get a benefit of performance. There are some directory that you can tell the cython to do to make the type inference more verbose. So you can see that what it actually do for type inference. So it knows that T is a type of double, and U is a type of double, and I is a type of long. So instead of doing it automatically and more like stealthily that you are unaware of, by using this, because it is doing things automatically, you probably will want to know what it does. So by using this director, you can actually see what it infer. If something is not as expected, you will see it right here. So it will do the automatic type inverse pretty good. However, the above syntax is not Python compatible. For one thing, this intx is not Python compatible. So this is also before the type hint annotation time. So there's a way to work around this syntax, but I mean, use a pure Python compatible syntax, but also do the annotation. So the cython figures a way to do so that you can first import cython and use a decorator to given the information of the type right here. So here, we are also using the infer type is true and infer type verbose is true, the same as above. The only difference is that we don't use intx, we use cython.locals x is equal to int. So everything is the same. But the difference is this code you can actually run by the Python, the C Python interpreters. You can feel free to import the cython, but if this is run in Python, the list decorator will do nothing at all. But if you are compiling it with cython, it will do the type of inference and compile it into C code. So let's see the C code, what it compiles into. You can see that all of these things are not calling the, although it has a funny variable name, it has a funny prefix and some like suffix right here. But anyway, it will have a very clean C language code. There's no calling of C API of Python. And this loop is translated into a Python loop, a C loop. So it is standard C loop. Despite of this funny and strange variable name, it is a total very efficient, clean C loop right here, like a for loop right here. And everything is assignment, no function, no API calling. The only thing that calls API is right here, because we have to use the print functionality. We are not using a printf, we're using a print functionality. So you can see that, okay, we still need to do some integer conversion into a Python format, to do some print function calling, to do some reference. So one interesting about cython is you don't need to worry about the reference counting. It will do it for you. So even though sometimes you are writing something more verbose like a C++ code, at least it will do the reference count for you. So in this format, the decorator will have something like define a class, define a function, define a function that is both works for Python and for in C. You can do some like a C inline or define a return type. So everything you can do in the cython syntax, you can do with the decorator. But a lot of this is replaced by the, you can replace this decorator by a more readable syntax in Python, that is type hinting. So we're doing the same thing right here. But it is a little bit, it should do it using like because this int is still the Python integer. You should use this like a cython, something like cython dot. I forgot. Let me check. Okay, so because we are using int, then it is still like a Python int. But if we are making it like a cython int, it will make everything white, make everything kind of you can say that the type of inference works. If you don't do that, it just use int, it will probably well, it still get int object, not an int, and this is a Python object. Let me try to make it into a string format, or maybe like import like. Okay, this does not work quite good. So the I and I is long, but other is still Python object. So this is not good enough. How about int64? Okay, not working. So you still need to make it like cython.int to make it we don't need numpy here. We don't we probably need cython here. Okay. This is something that you can do to do more like type. You need to do this directly. I'm not sure is this necessary. Let me try to avoid and to see what happens. Okay, it appears that in this newer version, you don't need that directly because type hinting is so so common that you don't actually have to use them anymore, and it seems to be turned on by default. So there are many different ways to do the annotation. One way is like above. We demonstrate a little bit different ways. And in fact, you can put all your definition in another file called the pxd file to separate everything to a pxd file, because the annotation, even with the Python type hinting syntax, it is a bit different than the usual Python. If you want to run everything in Python and also in cython to make the total compatibility, you should put every definition in a pxd file. That you can feel free to use the cython syntax to make it shorter, and you can make everything looks like a Python. Okay. There are also ways to define a class, but the class is a little bit more complicated because C++ has a class, and Python also has a class. So how do you make a bridge between them? In Cython, you can use cdef to define a C class, but if you use cpdef, it means this is feasible to both Python and C. The reason that we don't want to expose everything in Python is one reason is that we want to package things so that more secure, so we can decoupling the implementation to the interface. So that's one for the design selection. We don't want to export too many details. We want to only expose the things. So we don't want the leakage design leakage. So that is for designing purpose. The other thing is for efficiency, because if you want to wrap it to be used in Python, you have to have some wrapper, just like the CFFI. So it introduces more code and increasing the compile time and the complexity of things. So we only need this definition, we only use this definition when necessary. So here we export this XX into Python space. So you can okay, so AA is a thing, like AA equals to new AA. You can do that. So what is AA? AA is a object. So we can actually call the XX here. So it is print layer X here. And because the KK is public, if you don't use the public right here, it will not have access to it. But because it is public, so we can use public and the cpdef to make it see, make the Python can see these things. If we don't use cpdef, we use only cdef, we can still see a kkk. But if you are trying to call the xx, it will not visible in Python space. This is only visible because we use cpdef. If you without this thing, if you are using this thing, okay. I mean, sorry, cdef without public, we still need cdef. Then this one, xx is callable, but kkk is not accessible. So you need to use public to make some properties to be accessible, and you need cpdef to make the method to be visible in Python. Okay. So there are also some fuse type, which is kind of like a template that you can use in template. So because Python is use duck type, so one function can apply to, suppose you define, what I mean is when you define function like df like return fx, and you return x times 3, you can apply this function to a integer or to a floating number or to even to a string. They work the same because this code works for everything. So how do we do similar things in Cython? Because behind Cython is actually something similar to C++. So in C++, when we're doing something, we can use in a template to kind of like replace this type by other things, but using a different, because they are different type. So we compile a different function for different type. So in Cython, the similar thing is called the fuse m type. So we define a type called m type, which is one of the following possible type underneath. It is possible to be integer or a float number or string. So we define the return to be a same type, and the input to be the same type. So we can actually see that a to be x2 1, the float b to be x2 a floating number, and we can actually print it to be the string here. As you can see, the code is right here. Yeah, so we get everything we have, because this one is okay. So okay, print. you can see that it calls that the function which is print, no, okay, the fused here. This one is the fused function right here. So it is really long function, but it calls a function, and it calls another function right here, right there. So it print everything right here. So it will handle the template for you. Okay, so that's for the type annotation things. And another interesting topic is how do we actually write C++ in Python syntax. So sometimes you are trying to learn, or you are familiar with the C++, but currently the Python is your favorite language. That's probably one of my situations. But so you work with Python most of the time, but you still kind of like the Python Python sense. So how do you actually do that? So the thing is that you keep keep things in mind. Let me restart everything. Keep the C++ concept in mind, but you can actually write everything in cython. So one of the thing is that, okay, when we use the so here is a demonstration of writing similar things in different style. So one is using numpy, and everything is in cython. So we import numpy. When we use numpy, we are trying to almost every time we're trying to dealing with a block of memories and do something to an array. So there are similar things in cython that dealing with an array. So one way is to use the memory field. So suppose we have a numpy array right here. We can access the memory field, the array field to this array. And also we can define a C array. If you are familiar with C, we can define a C array. And we can have a C array field on this array, C array. So these are two different things. After we making it a array view, we can access it kind of like what you can do in NumPy, but you can use the loop. In NumPy, when we use the loop, this is a 3-dimensional array, and we add everything together. In the NumPy style, we are discourage you to use a loop because this will getting things slow. However, because we are thinking more in a C language style, so in fact the loop is actually encouraged because loop is fast. Especially we are able to use this loop in a more parallel way. We can modify code to make it run in parallel. So the loop is actually encouraged way to write. So we can write this thing in like this one. Sometimes it is easier to do because for some functionalities, it is difficult to actually write things in NumPy style. You already know what the algorithm is. It's just a loop or two loops. We have done that. But if you are doing this in NumPy, it will be very slow. However, in the Cython's world, you are feel free to do that because this is going to be very fast. I probably should make it -a to make a notation to let you see. So you can see that this code is totally white. So this is very fast. So if you are working with NumPy things, there is a thing called the memory field in Cython to help you to access to the buffer of these things to make these things run very fast. So memory field is to make a mindset to be very similar to NumPy array. So you can use NumPy array to do that to work with memory view. So you can see that we are working in memory view, but we are working on an ND array object. So we can kind of extend, if you are more familiar with NumPy array and working on NumPy array, you can do something occasionally in cython to make it faster, but difficult to do in NumPy. So you write in a faster cython code to make it faster and work with your data pipeline with NumPy. And a lot of times you don't actually need GIL, because after you are getting things into a memory view, like here, because we are working on the C space, we are not like we mentioned, because we mentioned that the primary reason that we need a GIL is because we are working with Python object. But after you get the things back into the C environment, you are working in C. You are not working in Python environment. So which is the white thing. So as long as this, the array, the memory view you are working with is alive, you're not mess up with the Python reference counting. So why not just release the GIL? So you can do that. You can actually do that. So we can release the GIL. We don't need a GIL, and we can do the things in parallel. So for here, we use a P range. This is a cython functionality, like a range, but you do this in parallel. And you can assign it to be no GIL is equal to true. So it will feel free to run the thread in full power. So let's try to test these things. So if you are using a single thread things, it will run in like 1.3 seconds. If we are using the no-GIL version of cython, it will totally get things like in parallel, and you only get like 163 milliseconds. So it is more like 10 times faster, like at least 6 times faster, like 8 times faster. I say that, and they can have even more optimizations. Sometimes it can automatically analyze the situation for you if everything is independent. For example, if we have an array here, all we want to do is find the summation of the items in this array. So we have a J here, and we do the J add by AI here. It will do the sum really fast and in parallel for you. So we add from Z to 99. The summation is, we already know that it's 4950. So if we add something like this plus 1, it will be like 50-50. So we know that. So it will, but if you do something more complicated, like you modify the value in this array, then this one is not so obvious to be embarrassingly parallelizable. So it will give you error. Says, okay, I don't know how to do this in parallel. So the cython has some ability to analyze the code and to make the most parallels for you, to make the code parallel for you. And you can actually set the number of a thread and do some fine tuning on these things. And you can do these context things to set the thread to set it to be 8, to kind of control how the behavior of the parallelism. So you can see that it is in fact in parallel. So we can run these 10 things in parallel. So it is not in the order. The 2, 3, 8 like 0, 1. So it is not in the order. And sometimes in this non-GAL part, you are going to use some Python functionality. When you are calling Python functions, you have to run the GAL again. So you can reacquire the GAL like here with GAL right here. If you are not doing this, it will either give you it will give you a error because you are calling something in Python. You are calling something in Python, but you are without GAL. It will give you some error for safety. But if you are very sure that you can call that, I believe there are something to work around with this to actually call it. But in this case, this is not a good idea because the print is actually need the GAL. Sometimes you know you don't need a GAL, but the print, if you're calling the print, you actually need it. So even if you find a way to work around with this requirement of GAL for print, you probably should not do it because the program is going to be crash. So if if you are using like other memory things like a vector or other things, if the things is also always have the same size, if your buffer is not changing size, because like we mentioned before, the GAL is for garbage collection, the reference counting things. But behind it is for memory management. So if you are not mess up with if you don't need to allocate new memories, then most of the time you can do the parallel without GAL, pretty safe, like here. You can even with using it with like here I'm using a C++ vector, but you can use other things like okay, it doesn't work right here. Okay, apparently the code has not updated, so I'm not going to use it. So let me check it. Okay. Oh, I see. Okay. All I need to do is probably just need this. Okay, so it at least it compiles, but okay, so let's forget about it. So I have to update the code, but the thing is, what I want to say right here is that if the memory is not an issue, you can probably do the parallel things. But if you are changing the memory, the things is different. So for example, here is an example that when you try to change the memory. Okay, here is an example. Even we are using a vector like we did before, but if we are push something into this vector, so here it is fine. We push everything in different order into this vector. So we need a GAL right here because we need some lock right here. If you're pushing something, you need a lock. So either with a GAL or with because this one is not a Python object. But if you are trying to modify the object to change the size of it, you probably will need a lock before you do that. Because when you add something, you modify the object. So if with GAL, this code can be compiled, but it will have
some issues, it will crash. Most of the time, it will crash because they are different threads are accessing the same part of memory. So it will cause logic error. So you can see that a lot of time it will just crash the code. But I mean, this time it seems to be okay because it only has some memory error. So I can still run it. Okay. But the time when I try it, it will actually crash. Okay, so but because this is not a Python, the factor is from C++ library. It's not from Python. So all we need is a lock. We don't necessarily need a GIL. We need a lock. So we can use OMP, Open Multi-Process Library, to OpenMP library to initialize another lock. So this is also a lock, but not a GIL. So you can run other Python code or other code. It will have in different thread, but they have different lock, so they are not mess up with each other. But if we are using a customized lock here, we can still do this. It's just because we are pushing something into a vector that is an array, so we change the size. We modify the same part of things. So we need a lock here. It's just we don't need a GIL. We can use we define our own lock here. This one still works. Okay, so in fact, you can see that we use some CPP library and use it in Python syntax. So in fact, in cython, it's very convenient to load like a CPP library like vector, like map and a string. All of this looks like what you can use in Python, but they are in a more efficient way because they are typed. There are some restriction. For example, if you are a vector, everything in the vector has to have the same type. Unlike the list of Python, they are very similar to each other. List and the vector are very similar to each other, but vector has to have the same type of every element. Because C++ is a typed language, kind of like the NumPy array, but NumPy array has a fixed size. The fact like the list, you can append or push something into it. So if you are familiar with these things, you can. I mean, if you are familiar with Python's dictionary, the list, you probably were very happy about the vector, map, or like the string right here, because they are just what you can do in Python. Okay, right here, do pretty much same. They just have different method in it. But how do you actually make it more even like a Python? I introduce some tricks. You can see that here is a Python code that we can do. In fact, you can do the definition in the PSD to make the things more like the vector more like a Python thing. So here is the same code. Although the original vector doesn't have a append method, but we can do some definition to make the vector more like a Python thing. So you can use the STL in CPP or C++. If you really more familiar with Python, there's a way to kind of rename the method name to it. Actually just a push, but if we rename it to be a append, it will look more like a Python. So the benefit of using this style is that you are using the same code in both in Python and in cython, and the semantic in cython is using the C++ standard library. Also, that's a benefit. But the drawback is that it is kind of unusual semantic. It's more like the meta programming that I was saying, that the Pythonic, it is not in the Pythonic philosophy, design philosophy, because you look like, okay, you are using if you are not aware this is actually using a factor behind you, if you look at this, you probably will think, okay, this looks kind of like a Python list. So what happened if something, they do have some different behavior. For example, you cannot append different type of things into the same vector as you can do in list. So you will get confused because it really looks like a list. So that's a drawback. So I don't think this is a good way to do that. But if you want to do so, sometimes it is very convenient to have some code base that can run in C++ and run in, essentially it is just C++ and run in Python. They have a similar semantics. Okay, so here, okay. Here is a way to use cython with pandas to enhance the performance of cython. So suppose we have a data frame like this one. We want to do something, we have a, B, and X. We want to do the calculus by divination using Riemann sum. So here is something like we have X times X plus minus 1. This is a function. We want to do like a Riemann sum, like sum of them together by defining, we have n partition and do like summation of S times dx, do these kind of things. So this is doable for pandas. We can use the apply method of the data frame to apply this function to do the integration. So in this naive, probably straightforward implementations, it takes like 84 millisecond, 84 ms millisecond to do so, 84 ms to do so. Okay, so let's do some profiling. This is do the p-run to do the profiling of the function to see which is the most time-consuming part. And you can see that the function, these two Python functions, integrate f and f, are time-consuming. So because they are time-consuming, why not just compile them in cython? So we can do that. So we simply use a cython to do that. You can also make it as extension, but because we are working with a notebook, this one is the easiest way to do so. But if you are not working with a notebook, you should do the normal way to compile it into an extension. Okay, so let's use this to compile this function together. But as you can see, because you have already know better, we are not given the type hint right here. So the improvement maybe just margin. So in fact, yes, the time from 84 ms improved to be 47 ms. It is significant, but we can actually do better. So we do give some type hint right here. We do some doubles right here, and the return also it has a return type, and also we use cp_dev because this one is the function that has to be visible in Python space. So we expose this function to Python. We don't have to expose this f function to be in the Python space because it is only called by the integrated f typed. So after we do some type hinting, we can actually do the automatic type hinting, type inference to make the code shorter. But anyway, we do the hinting right here. So the speed improve dramatically by almost tenfold, from 84 ms to 47 ms to 7 like less than 8 ms. So it is a huge improvement. Usually we stop right here, but we can actually do more. We can actually do more. So let's see what is a bottleneck right here. We run the prun again and see the most time consuming part is the get item and the get value. So this one is from the series. Series is the pandas series. The data frame contains several series. So the bottleneck currently is the series. We don't at the first step we don't want to modify these things to optimize these things, because when it runs like 84 ms, this is not important. This type, but after we speed up it to like 7 ms, this becomes the bottleneck right here. So we improve this one by, instead of passing the pandas series, we are passing a numpy array. We can even improve it by using a memory view like we do before. Also, here is what it does. It takes a numpy array right here as input and apply integrator. Instead of calling the pandas, it using the it converts the numpy array first. You can see that convert it numpy array first, and for every series it convert every series into a numpy array and run the function directly on it. So it is kind of a little bit over optimized because the syntax changed significantly. Before that, we just doing some lightly improve. Annotation. We already like 10 times faster, but this one is very significant modification. So we will have to ask whether it worth it. But it turns out it actually worth it. We improve our improve like 100 times better. Compared to the last version, we are almost like 9 times faster. So although this one looks a little bit different and a little bit less readable, but we got, compared to the original version, we are 100 times faster than the original version. Okay, so let's you can see how far we can do the optimization for the Python code, even though we are still sort of working on the Python, because every syntax looks kind of like Python, but we have 100 times faster. Can we still make it even faster? Yes, we can. We can add some cython directory to, because we already know these things are in the range. This is a safe code. We have already verified the things. So it doesn't have to check the boundary every so often. So we give this cython directory so that to indicate, okay, you don't have to do the safety check every time, because this code is written by ourselves. We are pretty sure this one is safe. So after add these two directly to make it a little bit unsafe, actually we just discard the safety check. It will have like 20% improvement. So I think it still got some improvement. We can do that, like using memory view, or do things like replace the numpy empty things. Yes, they can do that, but we'll already have more than 100 times improvement for speed, and the code is still itself is not too terrible. We only need, these two lines, only these two lines give us like 20% boost, so that's fair enough. Okay, so I think this example gives you an idea how to integrate the cython into your data pipeline to improve the performance like 100 times faster. So if you're doing one experiment like in 10 minutes, if you can do it in, I mean, if originally you have to do this in 100 minutes, after some cython involved optimization, you probably will finish your experiment in 1 minute. So that gives you a lot of attempts that you can try to adjust in different parameters. Also, that is a huge improvement. And the code is still quite readable. And it is mostly in Python syntax. Okay, I think I don't give the number a fair time share of it, but number is very important. Although I like cython a lot, but a lot of time, I mean, if you are writing C++, you are from the C++ background. Like I was writing a lot. I have written a lot of C++ code. Cython is probably one of the things that can give you some feel of C++ and integrate with Python. Also, Python 11 is not too bad. But numba is, if you are aiming for Python-like syntax, and you are most Python native person, you learn the Python is probably one of your first language. I mean, if the Scratch doesn't count, Python is probably your first language. Or like you are, if your first language is C language, but Python is more like the things that you are more familiar with, then probably numba is a better idea. Pandas does have a numba engine. Okay, but let me first show you the numba engine right here, so that you can do a really quick adjust to the pretty much the similar things. So this one is the original like data rolling things to do the sum over this window. If you change this rolling things to a numba engine, the first time it will do a compiling, so it will be slower. The default engine is Cython, but this is not the Cython thing that we see before. It just they write the big things in Cython, but they didn't compile this file in Cython. If you want to do similar things in Cython, you will have to compile this F in Cython. Then you will get some similar thing. But the original default engine is Cython. So if you are not specify the engine, the result will be like 4 seconds, almost 4 seconds. But if you change the engine in numba, the first time it will be slower, but because we are running on a large array, so it will be faster. And so the result is going to be improved. But the second time, it will be significantly much faster. It will only take like less than 200 ms. So this is more like 20 times faster. It's kind of like 25 times faster compared to the default engine. So the numba is your friend to compile things dynamically, and it integrates with the Python even better because you write true Python code, and you only add some decorator to it. And if you are using pandas, you don't even use the decorator because the number, the pandas will use the number automatically when it apply it. If you assign the engine to be number, the number really shines when it do things in parallel. So you can actually set the number of threads by using number. And when you're using the number engine, it will have a difference. Because if you are using it only as one thread, it will take like 347 ms. If you have 2 threads, it will faster. If you have more threads, it will get even faster. you can do the previous cython example in numba by using numba JIT, numba JIT. We probably don't have enough time to talk about detail of numba JIT. I will probably talk detail notebook in next time, but you can see that basically it is similar to the cython, and it will do because the JIT is doing things when we calling the function, so it doesn't require the annotation because it takes the the type of each variables at the time when you call this function. So you don't need to do annotation. So basically this is similar to what we do in cython, but easier because we don't have to do the annotation, and we can still get the same similar benefit like what we do in cython. So in this time, it like get 800 nanoseconds without the but the comparison to the original cython version is like 7 ms, which is 10 times slower. We do have a faster version that involving with numpy, but because numba the numba engine will do this for you, so it will have a similar performance like what we do for cython with numpy improvement. Probably the cython one is slightly faster, but as you can see that it is easier to write this code if you do this kind of thing. Okay, this code is shorter, so this is comparable to the cython version with the numpy. Okay, so cython is still faster. Okay, cython is still faster because this is comparable to the fastest cython thing we get is something like 600 nanoseconds or 800 nanoseconds. So it's comparable. So it's safe to say to that the number version is comparable to the cython. So another way to speed up things with number is to use number factorization things. So this is something cython is not that easy to do, but it is more like what the JAX can do. So we can actually writing a factorized version of a function, then apply it to the array. I mean, to an array or to a panda series. We can do that, so it will make things much faster, and we can write things easier because we can write the ufunc in numpy easily, which is unfortunately we probably will go into detail in next time. But we will add another tools. Talk about another tools right here. The NumXPR. It is also a tools that exists more than 10 years. And it is integrated with pandas. Although the speed up of NumXPR is not as dramatic as the cython and numba, but it is easier to use, more convenient to use. What is NumXPR? Basically, it is sort of like a NumPy replacement, but it can evaluate a string, so it can optimize the operations in in its space. So the NumPy is faster, it's very fast, but every time the NumPy operator is finished, it has to return the things back to the Python space. So for example, like the 2 times A plus 3 times B. after 2 times a finish, it will construct a numpy object, and after 3 times b finish, you can construct a numpy array object, and after them add together, it will construct another. But in NE, in principle, it can do this evaluation in one step. Like, okay, we do this operation component wise, and then finish. So it can do it in one run, not in 3 runs. So it can improve the speed a little bit. If this operation is more complicated like this one, the speed up will be more significantly. So it's a large speed up, like 20 times speed up for this case. But sometimes it's like 2 or 3 times faster. So although numba and it kind of like numba, and but the code is like in this string, so it is more restricted, and I think the optimization is not that huge, but it is easier to do so. So if you are just evaluating something simple, you can use the data frame pandas eval method to write your expression into this string and do the calculation. So if we have 2 columns like A and B, we want to add them together. You simple like doing like df.eval A plus B. Then you get a new series, which is the summation, component by component, element by element of these 2 series, of these 2 columns. You can do like df.a plus df.b. You have the same result, but this one is faster, or this one will be faster. So this is a simple way, and arguably this is more readable, because we know that column A plus column B. But you can see that this A and B, I mean the expression in this stream is compute in another word, which is a num-expr word. You consider it is, we're sending this into another word, let they do a computation, and they transform it back. Because the eval use num-expr backend, when it is possible, sometimes it is impossible, it will fall back to a Python backend. So when it works with num-expr, it will speed up your code. So here is a comparison of the data frame evaluation. It usually works better when the series is longer, which it means it has more rows in this series. So if you are working only with like 1,000, 10,000 or maybe even like 100,000 or rows, it probably doesn't. You probably doesn't need the eval, except if you want, if you think the eval things is more readable, then go for it. But the difference of the speed up is not that significant. But if you're working with more rows in the data, you probably can use the num-expr to speed up it significantly. Okay, another thing similar is PyPy. PyPy is kind of like the numba and the cython can do, but it is another interpreter. So in general, if you are not using something that is specifically for C Python, and most of your logic is in Python, the PyPy is a drop-in replacement of C Python to make things faster. Like in average, it is 4 times faster. In sometimes it is slower, but I think most of the time it is because some niche, and perhaps because of coding something with C API. But anyway, PyPy in general, PyPy is something you can try to make things faster. Another library is mentioned as CUPY. It is a replacement of NumPy. So if you are working with NumPy, not pandas, but pandas work a lot of pandas work can be worked with NumPy. So if you want to work with NumPy, but you want to using CUDA to do the computation, CUPY is something very suitable for this task. In some cases, I mean, it is mostly the drop-in replacement, but sometimes there are a little bit incompatibility between CUPY and NumPy. And sometimes even if it is replaceable and or replaceable with some slightly modification, sometimes there will not be a speed up. So the correct way use of it is to write a CUDA kernel for your operation. So if this is something, this is more similar to the cython or numba thing, but the code here is writing in CUDA, so it's more like a C language. So it is not exactly writing an extension, Python extension in C language, but it has similar purpose to speed things up. So if you can load some CUDA code in here, write a kernel, you can apply this kernel to the NumPy array. In here, the thing is already moved in CUDA. So it can kind of like the torch. If the things torch tensor is in CPU, this is NumPy array. And when it moves to the CUDA, it's like the CUPY thing. Just there are two separate object, so separate data type. They share of most of the functionalities, but in PyTorch they are in same data type, but in different device. But I think the logic is similar. A little bit different is it doesn't provide. I mean, CUPY doesn't provide the functionality of deep learning. It handles the CUDA kernel a little bit different than PyTorch. But other than that, if you are not working using a deep learning functionality, deep learning layers, it's sort of like PyTorch tensor, but they have the performance differences. So we have a lot of different tools. So this is a CUPY speed up graph comparing to the NumPy. So as you can see, we have a lot of different tools and frameworks that can use to speed up the NumPy array operations. And a lot of different choices. It is not easy to choose the right one. So in the current situation, I encourage you to try everything a little bit. There's no one solution that is better than everything else, and there's no one solution that is non-usable or worse. I mean, you can still use NumPy for most of the case, and use like PyTorch, Pandas, or not using Polars. That is still doable. But if you want to increase the performance, that is very critical in your application. There are a lot of different things to try, and sometimes one solution works better than the others. Some solution might usually works better than another solution, but I don't think there's one solution that you can definitely use. Like, I mean, numba, I prefer numba and PyBind 11, and I used to prefer, and I still like cython a lot. But I don't think one solution is definitely already dominated the area or better than others. I haven't used CUPY a lot. I only tried it a little bit, and for the application I'm using, it is not improved the performance much, but I will still consider it when it fit the need. And probably always some using the PyTorch tensor instead of using CUPY sometimes. So I will try everything. So that's why I try to write a code that can fit in different framework, like what I did for the C++, Cython things. I think that's one choice, that you make your code to compatible with different framework, so that you can try different things and to see which one works better for you. So next time, I will continue to talk about numba and talk about polars and Rust.